So hello, our lovely community. Okay, I think we can get started. Okay. So hello, our lovely community. Who you can hear right now, this is Elaine from Seed. We here for this workshop introduction. I am marketing manager from Seed and work with Wire Terminal community for like 2 years long. So hi everyone, and also hi Benjamin, hi Huiying. Okay. So we're quite excited to meet you here and we'll terminal hands-on workshop about building TinyML projects in a no-code way with Codecraft. So actually we received like hundreds applications for apply the web terminal and we already have sent 50 devices to random applicants. We appreciate a lot your support and interest in wire terminal. We love a lot this warm community. So today we have Huiying Lai, our application engineer from Seed. She will introduce the Edge Impulse powered graphical programming platform and use it to train the models with wire terminal onboard sensor. So, and also we also have our friend Benjamin from Microsoft Azure IoT. Besides using onboard sensors like buzzer, light sensor, accelerometers, you can also explore over 300 Go modules for different applications. Codecraft is more than a toy, but it's an useful tool for beginners, educators, and students. We're thinking about when beginners first enter to machine learning, they might need experience with data science, algorithms, and programming skills. So Codecraft TinyML will give all educators and the students an easier visualized way to understand how machine learning really works, problem solving, logic behind the code, and also build the useful applications you can apply to real world life, which is actually learning coding without any lines of code. So Benjamin spent a long time trying to perfect this machine learning recipe. I believe you will never want to miss the chance to read his project on Make Magazine Volume 77. You will find his artificial nose is featured on the cover. I will also attach Benjamin blog link on the site. Follow his all open source libraries and tutorials. You can actually build your actual nose. So you will find hundreds of wire terminal projects, classrooms, and lessons in this community we've created in these 2 years. So I want to quickly introduce wire terminal if you happen to jump in this workshop and not know about wire terminal yet. So wire terminal is compatible with Arduino and MicroPython, built with microchip SAMD51 with Wi-Fi and Bluetooth support. It is an all-in-one IoT device with screen, accelerometer, microphone buzzer, micro SD card slot, light sensor, and infrared meter. So thanks to Edge Impulse imaging, makes this biggest embedded machine learning event happen and bring us together. So Edge Impulse make it come true for building a model in just 5 minutes with the real world sensor data. You can training the model, learning the models, and understanding the real-time information on their platform. But now, is that possible to acquire data, train, and deploy the model with only drag and drop the blocks? My answer is big yes. So now I will give the camera to Huiying. Let's right kick off to TinyML with Wire Terminal and Codecraft.
Hello, everyone. Thank you for joining our workshop. I'm an application engineer working at C Studio on machine learning application for embedded devices. I'm in charge of integrating wire terminal C Studio hardware for TinyML into Codecraft, a graphical programming platform. Powered by Edge Impulse, Codecraft provides a user-friendly web interface and toolkit for the whole TinyML pipeline, starting from data collection all the way up to the model deployments and extensive use. seed team endeavors to create an open platform for global developers to show to lower the threshold for using TinyML. So this workshop is graphical programming for TinyML. The easier way to start with embedding machine learning. I have a partner, Benjamin, who will give his presentation later. At the beginning, I would like to show a video. Letter S, letter E, and letter D. We can use while terminal to identify the motion of these three letters so as to form our company's name. How to do that? Let's find out the secret of it during our workshop. First of all, we need to prepare three things: website, device system, and while terminal. If you don't have the device system, don't worry. When the device system is needed, a pop-up window in the website will be shown to guide you how to install it. Then we can start our workshop. What is TinyML with while terminal and Codecraft? What is machine learning? Machine learning is a branch of artificial intelligence that focuses on building applications that learn from data and improve their accuracy over time. This process is carried out without using traditional rules-based programming. Machine learning enables machines to work by observing, classifying, and learning from mistakes just like human beings. What's TinyML? Tiny in TinyML means that the machine learning models are optimized to run on very low power and small footprint devices, such as various microcontrollers. As we all know, microcontrollers has a lot of advantage. Ubiquitous, small, consume small amounts of energy, and are cheap. Thanks to recent improvement in model optimization and emergency of frameworks, especially created for running machine learning model inference on microcontrollers, it has become possible to give more intelligence to these tiny devices. The devices with the embedded microcontrollers can be used to give new lights and minute to old sensors, such as using an accelerometer installed on a mechanism for anomaly detection and predictive. The possible of the TinyML is truly huge. Of course, it has the limitation. The main limiting factor is the RAM and flash size of the MCUs. No matter how well you optimize, you won't be able to fit that Euro 999 into the tiny microcontrollers. So we need to clearly know the size of the machine learning model we have built. In other words, what kind of mission we can use to achieve TinyML. Here we will use our while terminal and Codecraft powered by Edge Impulse to achieve the TinyMLs. Let me detail the while terminals and the Codecraft. The while terminals runs at 120 MHz or up to 200 MHz, 4 MB external flash, and 192 KB RAM, having an advantage in building TinyML project. It supports both Bluetooth and Wi-Fi, providing backbone for IoT project. And the while terminal itself is equipped with 2.4-inch LCD screen, so that with the simple program, we can get the display we want on the screen. The while terminal has a built-in module, accelerometer, microphone, and light sensor, and so on. On top of that, it also has two multifunctional group ports for group ecosystem and 40 Raspberry Pi compatible pin GPIO for more add-on, so that you can build your TinyML project with your creation, giving new light to all sensor. What is the group I just mentioned? Group is a modulated, ready-to-use tool set. it takes a building block approach to assemble electronics, compared with the traditional complicated learning method of using a blackboard and various electronic components to assemble a project. Groove simplified the learning process significantly. The Groove has the uniform interface, so just plug and play it. Every Groove module adjusts a simple function, such as a simple button or a more complex sensor. Software-wise, we will be using Codecraft, a graphical programming platform powered by Edge Impulse. It's easily accessible for beginner using Codecraft. It provides a beginner-friendly yet powerful web interface and toolkit for the whole TinyML pipeline, starting from data collection all the way up to the model deployment and extensive use. So how to use Wall Terminal and Codecraft to achieve TinyML? Let's quickly go through how to use Codecraft to achieve our machine learning journey. First, please open the website. Click on the icon of the Wall Terminals and you can see this interface. To create and use the model, you need to log in. And if you are a new user, you need to sign up first. Then look at the left of the page. All the machine learning process are composed of 4 steps. So we can build our own TinyML application step by step, from model creation and data acquisition and training deployment, and then programming. Model creation, the first step of the TinyML. You can create a model here by selecting the sensor you are going to use. As you can see, Codecraft provides frameworks, 3 Wall Terminals built-in sensor and a Groove. Click the corresponding icon to create a model using a particular sensor. After creating a new model, the interface will jump to the data acquisition interface automatically. And look, the default data acquisition program has been provided. You can upload it directly to start your data acquisition journey. Of course, this default data acquisition program is related to the default labels. Here, you can see that. You can add and delete labels. To add a custom label, click Add. When you use a custom labels, you need to change your data acquisition program too. Click on Introduction to Data Collection Steps. A pop-up window with the data collection process will be showed. Pay attention to the Wall Terminal button location, A, B, and C, and the animating GIF here has been accelerated. The actual action can slightly slow down. Please note the red tips, which help you with your data collection process. And you can point your cursors over description text for more detailed contents. Once the Wall Terminal is connected, click Upload. This action will upload the data acquisition program. Start and finish your data collection according to the Wall Terminal's displays. This red circles means data is being collected, and the OK means data collection is complete. When you think the data set is enough or the data acquisition can be finished, click on Training and Deployment. Training and deployment, the third step of the TinyML. You can select the suitable neural network size, small, medium, or large, and Codecraft provides default parameters values for each scale of the model. You can also set a number of the training circle, the minimum confidence rating, and the learning rate by yourself. And you can observe the data you have collected here and the model training report here, model training report. You can observe the training result, including the accuracy, loss, and the performance of the model on wild terminal. And the log training log here. The log screen display a training log. By observing the log, you can deduce the model performance. And I would like to talk more about the training circle and the learning rate. The number of the training circle is also called an epoch. It specifies the number of the time the entire training dataset passed through the training process of the algorithm. With each epoch, the internal model parameter will update, which may help the model perform better. The figure here is show that here is the screenshot of the log, the training log from here. And we can show that with each epoch, its accuracy has changed. And after each epoch, the neural network internal parameters have changed too. And what is the learning rate? Actually, learning rate is a very important hyperparameter. If is a very important hyperparameter that controls the change to the model in response to the estimated error each time the model is updated. Choosing the learning rate is challenged because if the value is too small, it may result in a long training process, whereas too large values may result in an unstable training process. Just take the perfect model as the bottom of the values. If the learning rate is too low, we don't know when we can reach the button, our targets, and we may reach a fake value. And a good learning rate takes a proper time to reach the desired goals. And the high learning rate, we always miss our way to get into the value entry. And the learning rate is very high. Okay, it's a very poor behaviors. But different tasks, different models require different learning rate. So we need to change the learning rate according to the specific task. The default parameter values provided by Codecraft for each scale of the model is the parameter recommending for this task. So you can try them first. Now we know how to set the parameter, and after training, we got the training result. If the training results are not satisfactory, you can go back to the first step of training and select another side of the neural network here, or adjust the parameter setting here. Then train again until you get a model with satisfactory result. Click on the model deployment here to deploy the ideal model. Then it will jump to the programming interface. You can complete the program by dragging and dropping the blocks. TinyML with the wild terminal free course for beginner is available. The course provides the most concise sample code. You can find the corresponding blocks according to the block color. Of course, you can program by yourself. Then we can use wild terminal to test the model we have trained. In conclusion, with these 4 steps, we can build our own application. Remember the application I showed at the beginning of the workshop? The whole process costs 40 minutes due to the time limitation of this workshop, and for better demonstration of the process, I record the operation and illustration in advance. Open the website, click on the icon of the wild terminal. Click on model creation. Click on motion recognition because we use the wild terminal's built-in accelerometer. Enter the name according to the requirements. See it here. Click on OK, and it will jump to the data acquisition interface automatically. As the sample application shows, we use three motions: motion S, motion E, and motion D. So we need to modify the labels. Click on the labels to be modified. Enter a new name as here and click on OK. Three labels are not enough. We also need the motions idle and other motions, so I should tell the model that these kinds of motions should not be classified into the three target motions as E and D. So in the label screen, we click on Add, label name idle. Click on OK. Finally, we got five custom labels we want. Then we also need to modify the data acquisition program. Select the block and change the block name from free to S to E. We also need to add new blocks so as to clear the data of two other motions left. Luckily, our while terminals has five-way switch. Five-way switch here. Copy and paste. Control C and Control V. We also need the block sample data. C and Control V. If we use five-way switch up to sample the data. And use the five-way switch down to sample the data others. Finally, we got a program which can sample 5 labels. Upload it. Usually, it takes 10 seconds to upload. Once the program is upload successful window will appear on the screen. So we just need to wait for it. Click on to close it. And it's time to sample. Pay attention to the while terminal's button location. A, B, and C. Press button A to start that motion S. Press button A again as we need to collect enough amount of data set. Click button B to start collecting motion E. Okay, press button C to start that data D. And we use five-way switch up to clear the data idle. And then we use the file switch down to collect the data others. Others motion. Others motion. Okay, now the data acquisition is finished. Click on training and deployment. In this case, we are using large. It will take quite a long time to train the model. And then set the training circle to 20. Pick other default parameter value. Click on Start Training. The duration of loading varies depending on the size of the selected neural network and the number of the training circles. Larger is the network size and the number of training circles, the longer it takes. You can also infer the waiting time by observing the log. Epoch here indicates the total number of the training run is 20, and 11 runs have been trained here. Okay, the train model job is complete. Look at the model training report. Wow! In the model training report window, you can observe training results, including the accuracy, loss, and performance of the model. Accuracy is 100% and the loss is 0.01. Here, so I'm satisfied with the training results. But actually, as showed in the last training performance, we got a 100% accuracy. This is not necessarily a good gesture, as it might be a sign that the neural network is too true for the specific data set and might perform poorly on new data. Over 15 makers, a statistic model is said to be over 15 when it starts learning from noise and accuracy data entries in our data set. It happens when you have a large model and a relatively small data set. In this case, the model memorizes all the data points without generalizing and perform poorly on the new data. But I tried the model first to check whether it's over 15. Accuracy, loss, and perform accurate model. Run screen automatically. In the programming interface, click on Use Model to use the deploy model. Here, you can see it. I want to use this block, this block, this block. This prediction, this one. Okay. Okay. Try to use your model by writing the following program. Okay, click the upload button. The first upload time is really long. It increases with the complexity of the model. The upload time for smaller model is about 4 minutes or longer. depending on the performance of your machine. So we should wait for it. Then you can check your model anywhere you want. Motion S, motion E, motion E, motion E, motion D. Motion D. Yes. Congratulations, you have done it. Here is the complete code I have used in the video. A little change so as to display the words in the center of the while terminal screen. I still want to share more demo with you for detection. Use while terminals built-in accelerometer to record the dataset of daily activities, working, running, and fault, then train the model to develop a simple fault detection device. With the TinyML and while terminals Wi-Fi function, the family can be informed when a fault is detected. And the next one, the daily activity recognition. Like all patterns, some activities are easier to detect than others. For example, cyclical movements are much easier to detect compared to non-cyclical activities. Walking, running, cycling, swimming are examples of cyclical activities, whereby the repeated nature of the movement around allowed machine learning to be quite accurate in detecting these activities. If you review the market of wearables, you will see most devices target these types of sports activities. We can make our while terminal become a smart sport detection, detecting going upstairs, downstairs, and walking. And we also use the built-in light sensor to build a barcode recognition. The barcode is a combination of black and white bars, usually representing a series of decimal digits, with black and white bars reflecting light differently. Different barcodes can have different line sequence. So we can build a barcode recognition device according to these features. And gesture recognition of rock and Vulkan. This is an application built by a designer of our company who knows nothing about TinyML or machine learning and doesn't have any programming background. You can experience his application in the recommending apps. And the voice activates robot card using voice to control the car, and the color command using voice to change the color displays of the screen. These are two eye-catching applications built by two makers, and I add a link here who they inspire you to. If you have developed an interesting TinyML project of your own, please let me know. I have not used the while terminals Wi-Fi function. If you need to use that, please update the wireless code firmware. You can check the link here to get the details of the operation of updating. My run is finished. Any question? I hope I can help you with the question in the last 5 minutes of the workshop. And then welcome my partner, Benjamin, who makes an interesting AI notes.
Thank you. Yeah, well, with the time we have left, well, first, thanks for the great presentation so far. It was great to hear about Codecraft. I've actually been using it a bit myself, and so I want to tell you a bit about it. Make sure that you all share your questions in the chat. And something that I wanted also to mention is that we lied. We said that it takes too long to show you the stuff in real time. Hence why we show you the video of Codecraft in action and how you can use it to train models based on accelerometer data, what I want to do is a live demo of a project you may have heard about. And I actually have another workshop coming up in just an hour, I think at 11 a.m. Pacific, where I go into even more details about this artificial nose. It's this guy, it's using the Wio terminal as well. And the idea is to show you, when I started the project about like a year ago, I used whatever was available back then, and Edge Impulse was already around. But in terms of actually programming the brains of the artificial nose, it was a lot of embedded code, right? And not necessarily fun code. When it comes to TinyML specifically, you're manipulating a data pipeline, right? You're acquiring data from X, Y, Z sensors, feeding the data into some kind of neural network, something that hopefully you've built through Edge Impulse or other tools. And it's now becoming easier and easier to build the actual neural network. And then you have an output, and the output is also data, right? It's kind of a signal that you want to route to somewhere. The signal might be some kind of visual feedback to your end user in the form of something being shown on the LCD display, like we saw in the demo just before, some kind of audio feedback, or it could be also something that taps into Internet of Things scenarios. And beyond the buzzword, the Internet of Things combined with TinyML, essentially the idea is that you build and you use TinyML for what it's good at, running like potentially super complex AI on very small MCUs, potentially battery powered, and you have like really efficient intelligence. And the whatever insights you extract from the at the edge, you may want to route to your good old information systems, right? And to the cloud, so to speak. But like essentially you detect maybe with an artificial nose, you detect when some bad smell or dangerous smell is detected in the kitchen. And it's not only about ringing a bell in the kitchen to alert the users that are in the house, but also potentially send something more remotely, right? More something over the air, right? So in terms of demo, what I want to show really is how I took or how I can take the Wio terminal plus a gas sensor. That's also something that you can get from Seed. It's a multi-channel gas sensor that can smell or detect rather and measure the concentration of carbon monoxide and volatile organic compounds, things like that. And so I want to take this device, this sensor and this microcontroller, turn it into a nose, and more importantly, turn it into a connected nose, right? And so I'm going to share my screen in just a moment. I want to just make sure that I have the right, the right tab there. So let me share my screen. So the idea is that I want to connect it to the cloud, and not only the cloud, but to an IoT platform. What is an IoT platform? In a nutshell, it is some kind of backend service that allows you to centralize all the data that's coming from a wide variety of assets that you may have. Some of them might or might not be running MCUs, right? It can be maybe something more, slightly more beefy and more powerful than something like the Wio terminal. But more often than not, what you're connecting is effectively really small devices, really constrained devices, and using either Wi-Fi, cellular, or like at least using some kind of internet protocol. You're connecting your devices to the cloud, right? And the platform, the IoT platform, provides you with a way to do that in a scalable fashion, because connecting potentially hundreds of thousands of devices, it's can be a tricky business. You want to do that in a secure way, and you want to do that in a way that also opens the door to integrating with solutions out there, right? It's not just about routing data to the cloud, but it's also making sure that the data flows to your database so that you can archive all the data. So you want the data to flow into your rules engine so that whatever insight, whatever signal you picked up from your TinyML device, you turn the signal into something way more complex, right? And into some kind of actual business decision, right? So what we're going to use is the Azure IoT Central platform. We will be dropping a few links in the chat, but essentially, if you go to azureiotcentral.com, you can get started really quickly, right? And so you can set up your own instance, your own environment for connecting your own IoT devices, right? And you may want to start by using some pre-configured solutions, right? If you're aiming at building some kind of digital distribution center, then we might guide you towards some kind of approach in terms of how you would structure your business data, how you would present it in the form of dashboards, because once you have connected devices, one thing that you often want to do is have some kind of dashboard that gives you a way to look into how your fleet of equipment, how your stores, your factories, your connected cars, whatever it is, you want to have a look into those, right? So what we're going to do essentially is rather than creating an existing app, which I could frankly, and I could just click here, create an app, I'm going to reuse an existing one. And that's going to be one aspect of the solution, right? We want in the cloud where a lot of the integration with, existing information systems happens. In the cloud, we want to rely on Azure IoT Central and making sure that we have sort of a counterpart for our nose, because on the other side, at the very on one hand you have the cloud, and at the complete opposite side you have what one would call the edge, and the edge devices, in our case the nose, and we want to connect both, right? And so when you start with IoT Central, here it's not like a complete vanilla deployment of Azure IoT Central, but it pretty much is. Like I did some very basic customization to get ready to build some kind of connected noses solution, but I didn't do much. I don't even have that many devices connected, frankly. So the goal in the next few minutes will be to build a connected nose virtually, like pretty much from scratch, and making sure that it is effectively connected to IoT Central. One information that we will need is we created our own platform, our own IoT cloud instance, and it is unique, right? It's not like we want, it's not like I want you folks to connect your devices to my IoT platform. Like it's mine. It comes with its own set of credentials and secrets that only I know and that only I will flash right deep into the devices that I will be building. But this information here, the so-called ID scope and the key that I could see if I were to click here, those are my secrets. Essentially, this one is not so secret. Here, I have an actual secret that I don't want to share with you guys. That's what I'm going to use to build and to effectively connect the nodes. So let's start essentially from scratch. So I have a Wayo terminal. Where is it? It's here. Wayo terminal here. I want to make sure that I connect it, right? So let's try and do just that. So going back here, and let's open Codecraft. Codecraft, in case you didn't realize, everything's happening in the browser, right? So it's that's a great back to my intro earlier about the fact that when you do TinyML, you usually care about the data, right? You don't necessarily care about embedded programming. What you want is turning raw sensor data or raw data in general, turning that into some more meaningful signals and routing that information to business applications. And so it's great to not have to necessarily install embedded IDEs and C compilers and so on and do everything from the browser. So I'm going to do just that. I'm going to start with creating a new WIO terminal project. Let me just make sure that I actually start from scratch. For some reason, the context is not right here. New WIO terminal project, blank sheet, blank program. So we want to build something literally from scratch. What I did beforehand is go through the process that we saw earlier during the presentation of creating my own model for sense, right? And so detecting things like ambient air, coffee, whiskey, and training a model against that, right? So training a reasonably small model in the end, but a model that is that seems to be accurate, with the caveat that we mentioned that having 100% accuracy might not be a good thing, but I don't care. It's just for the sake of the demo. The good news, another way to look at it, is taking just 20 seconds of smelling coffee, smelling whiskey, smelling ambient air. It's still enough to have a model. It might be an overfitting model, but it's still something, right? To be able to train a model with so little data, right? So that's what I did as sort of a prerequisite. But then, let's really start from scratch. We have this model that already exists. For some reason, the context here, some of the stuff that we're going to show today is not fully released. So I might hit F5 and refresh the page more often than not. But this was the last time. Let's say this was the last time I was refreshing my my page. So building a connected node, there's going to be two aspects to it, right? It's going to be there's going to be some TinyML aspect to it, and running, like getting data off the gas sensor and running it through the TinyML model and running some inference. And the other aspect is going to be connecting to the IoT platform, to Azure IoT. So setting up a Wi-Fi stack, connecting to Azure IoT Central using the secrets, the credentials I was mentioning earlier, right? So we need to do both, and let's just do it, and let's do it live. So there's this sort of generic pattern, just like in Arduino, where we have, and here, hopefully you can start that we see and we visualize already the flow of the program, although the program is not doing much, but we start by setting up the display, making sure that we have a screen that's properly initialized. I actually have even a splash screen on the SD card in my WIO terminal. So let's display the splash screen, and then let's start connecting to Wi-Fi, right? So setting up the Wi-Fi SSID and password. So the SSID I'm going to put, and the password I'm going to keep it for later, so that I don't share it on screen. And then what else do we have? We have a block to connect to Wi-Fi. Can I put this block here? No, I can't. It's meant to be part of a control structure. So it's essentially, let's try and connect to Wi-Fi. And if it works, then let's continue the initialization process. Let's initialize the connection to IoT Central. We have this scope ID that we saw earlier, the primary key. I'm going to do that off screen. And the artificial nose identifier, I'm going to call it, I don't know, artificial nose 007. That's that's the name it has. We initialize the connection, and we effectively connect, right? And if that works, maybe we do we play a tone on the speaker. And then once I have that, I'm effectively connected to the cloud, and I want to use and leverage the fact that I can run an infinite loop here in that particular section of the program. And essentially, I want to run a loop every 3 seconds, for example. And every 3 seconds, I want to get data from my artificial nose model and then publish the data to Azure IoT Central. And assuming that works, I actually want to also have some kind of visual feedback on the screen so that it says data sent. And maybe I do a beep as well. I like beeps, playing a tone on the speaker. What am I missing? I'm just missing the credentials, I think. So I'm going to save the code and before I forget, I'm going to go off screen for just a tiny bit and put the credentials, and then we're going to upload the code, right? So let's, stopping my share for just a tiny bit. And please make sure you ask your questions in the chat. So primary key, and then the password is, where is it again? There we go. All right. Share my screen again. And you can see the credentials there somewhere on the right far. So what's next? Connecting to my Wio terminal. So I have my Wio terminal. Sorry for, there we go. So Wio terminal is here, and I'm gonna connect to it. Connection successful. Again, I'm doing this from my web browser, so it's pretty unique. And I'm connected, and I just need to upload now, right? So I'm going to upload to the Wio terminal connected to COM8, and let's see how that goes. Let me see. Are there questions in the chat? Maybe while it's uploading. I'm sure I see questions, but Jenny, feel free to drop them directly in the Zoom chat in case I missed any. Maybe we'll have, so you guys can still pay attention to the Wio terminal. Eventually, it's gonna be reprogrammed. Maybe in the meantime, I can give you a very quick tour of Azure IoT Central. Where is my IoT Central tab? It's here, I think. So yeah, while it's flashing, essentially once that's done, the things we're looking at is being able to not only have some kind of live dashboard. If I were to look at another device that I've been tinkering with in the past few hours, we can see the raw telemetry, right? The raw sensor data coming from the device, raw sensor data read out of the gas sensors, things like that, right? So we want to be able to look at that. We want to be able to potentially implement some rules. If the nose tells me it stinks, then I want to send someone to clean the room, right? If you're thinking of some kind of scenario where you do remote management and you're in the business of doing facility management, having a sniffing device that does just that can be super powerful, right? But you don't want the device itself to be responsible of sending directly the SMS to whoever, right? Because that person might not be the same from one day to the other. Who is responsible to clean such or such room in the building is a very dynamic kind of information, right? So you want to rely on the cloud for doing just that, and that's that's what you would do with IoT Central. So let's see how are we doing upload wise. It's still going. I think earlier in the presentation we were saying that it can take a while to one, compile, and two, get uploaded to the device. But I'm fairly confident that it will eventually succeed. Let's see, certain Sophia, you were asking a question earlier about what's a good number of training cycles, what's the learning rate. In general, like you experiment with, like, first you want to train your model with as few training cycles as needed to get you a reasonable amount of accuracy. But if that's not working, then it's either that you don't have enough training data, or your model is not well architected and well designed, and or you need more training cycles. But usually tuning those parameters can require some time. This is where you may want to rely on some edge impulse tooling to auto-tune such parameters, right? Like automatically, edge impulse could actually figure out what's a good learning rate, like I mean, what's a good number of epochs and things like that. So it's it can save you some of the manual adjustments. I'm going to go full screen. Oh, I'm already full screen with the camera. Upload is successful, and the device right now, it's effectively the upload succeeded. It's just doing some quick checks in terms of Wi-Fi connection and stuff, but it should take another second or two for the device to effectively connect. So let's keep our fingers crossed. I'm pretty confident it will work. So let's see. I'm just going to check real quick if I didn't have the blank here. No, it should be good. The demo worked earlier. I'm actually almost tempted to switch to another weird terminal that I have, for which I know for a fact that the program on it works. And thanks, Jenny, for the reminder in terms of how much time we have left. Hopefully, this is just enough time for the demo to work. So what should I do? Should I switch to the other weird terminal? I think I will. Okay, so I have another weird terminal where I flashed exactly the same program. So let's see. It's here. It might not be called artificial nose 007, but you get the idea. I hope the issue is not something as stupid as I just have some guests who arrived at home, and it might be just my Wi-Fi that doesn't work that well. So let's see, and let's keep the fingers crossed again. Come on, you can do it. All right. I'm not sure what's happening. So I guess this will be my shameless plug for almost all of the second half of the workshop, which is again in it's actually in 30 minutes now. At the top of the hour, I will be covering even more in terms of IoT integrations. I really encourage you guys to join that one. Elaine will be dropping a link to and a few links in the chat, or if she can't, maybe Jenny can be the proxy if we cannot share links. But there's some great resources. IDE.tinkergen.com to access Codecraft, and yeah, I mean, check it out. Feel free to ping us and find us online. Seed Studio on Twitter. I'm Cartban on Twitter, and see you soon. See you at the top of the hour. We'll keep an eye on the demo for the next few seconds until we wrap up. But sorry that for some reason the the wow effect wasn't there, but if I figure what the issue was, I will post and share on social media. It's always nice to learn what contributed to a failed demo or to a partially failed demo. Thanks everyone. Thanks Elaine, and thanks to the team at Seed for the great collaboration. And enjoy the rest of Imagine, everyone.
So thanks everyone. We will wait you on the Twitter and also the Discord, and you can ask any questions on the demos, and we'll keep updating. Thank you.